Okay, so how are you guys doing? Everybody doing all right today? So today we're going to get into Navier Stokes equation, and we're mostly going to spend our time deriving something that winds up being relatively innocuous, but the path to get there is kind of bizarre. But you have to go through that path to get to something innocuous, and it's not actually innocuous; it's complicated. So let's get started. Does anybody have any questions about anything? There's a reading due next week, and the reading is on the stuff that we're doing today. Normally I like to have the readings before I talk about it, but I wasn't on top of my game to get this assigned, so that's what happened. And that's okay, because this stuff is weird, so when you read it, it'll be less weird. Instead of the reading being confusing, the lecture will be confusing. Hopefully not too confusing. Okay, so d by dt of v plus v dot grad v equals minus 1 over rho grad p plus nu del squared v. Vector, 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 vector. Okay, so we haven't really talked about the behavior of what del squared really means yet, and we will. But this is the Laplacian operator that is just basically the three-dimensional second derivative. And I'll show you where it comes from and why it gets there in a second. So what we're going to do is basically derive this term here. So remember that this term is just dv dt, and this term is just pressure. And this term, what is this term? So when I have a flow, if I shoot a jet of water into a pool of water, that's going to be moving past the water here and moving past the water here. So it's going to transfer momentum upwards. So if I just have one infinitely small, well, okay, not infinitely small, because that doesn't make any sense here. You have to have some finite volume. You've got to be bigger than a bunch of molecules. But a very small thin stream, if I shoot a very small thin stream, that will entrain the fluid next to it to accelerate. That makes sense, right? Like if you rub your hand on something that'll move, it's going to start to move with you, right? So we had started by saying that the force, I'm going to put this over here so I have it, a tiny little element of force is going to be the pressure tensor, this is the I direction, Pij times dAj. So this is similar to the pressure that you've dealt with a bunch of times. So this is just force is pressure times area. But now we're generalizing it so that it's not just the one pressure. Now we have multiple directions that the pressure can act in based on what's going on. So now the pressure is this complicated thing that can have stuff happening in the x direction due to things going on in the y direction. I'll explain what that means in like 4 seconds. But this is our general force that we're going to talk about. And when we were just considering the isotropic gas pressure, the standard pressure, then this becomes dF equals P dA, little a, and these are vectors, and then we do an integral, and then we get over volume. This is already over d area, so this turns into a volume integral, and we get F equals grad P, and I need a minus sign there. Is everybody comfortable with this? We getting this gradient here. So we're going to do a similar stuff, but now we've got things that can happen in both directions. So now I'm going to write my pressure tensor. Pij is going to be my isotropic gas pressure that you're used to, PV equals nRT pressure, times delta Ij plus pi Ij. And this is now the shear stress. So stress is any sort of differential force on a body. So If I have a cube, I can have a compressional stress by pushing on it from both sides. I can have a shear stress by pulling on it in opposite directions and opposite sides. So stress is just kind of, think about that as the spatial distribution of the forces that are going to act on the body. So now we're saying our stress, and you can think about this also as momentum transfer. So we're going to think about the stress as momentum transfer. So the momentum transfer of the I component of momentum in the J direction is going to be minus mu times dvi dxj. So let's be specific. Let's call this, so this is now y, and this is now x. We're talking about dv x dy. So let's draw this a little better. So what this winds up doing is setting up layers where the velocity gets smaller the further away you go from my original string. So I have Vx is in this direction, and I have a gradient of it in this direction. This is why it's a tensor, because I have gradients in one direction of velocity in the in a different direction. Does that make sense? So let's talk about this mu. And I'm actually going to not talk about mu. I'm going to talk about nu. So nu equals mu over rho. And mu and nu are both coefficients of viscosity. And when I'm talking about momentum, I need mu. And when I'm talking about velocity, I need nu. This will become more clear for a second. So I'm going to talk about mu, and this is my coefficient of viscosity, because really, at this moment, I'm talking about momentum transfer. It'll turn into a velocity in a second, but that's just dividing by the density. So it's not a big deal. I just have mu and nu, and one's got a density and the other one doesn't. So mu is the coefficient of viscosity, and dv dx is what the flow is doing. Mu is a property of the fluid and a property of the thermodynamics of the fluid. So let's talk about what this means for a second. So nu, which is related to mu, but nu is how much velocity you're probably going to carry times how far it's going to go. Sorry, the squirrel brain interrupted me. Told me I was totally talking originally. But I have to ignore the squirrel brain because I'm not. So nu is how much velocity a particle is going to carry times how far it's going to carry. So if you think about these parallel streams, and just think about this as a pool jet going into a pool. That's a good analogy. I have random motion. So the particle velocity is not just in this direction, it's in all random directions. Right? So what is a typical particle velocity? I've got my velocity of my stream, we'll call it v, and I have the velocity of a particle, we'll call it vp. What is the typical velocity of a particle in a gas?
Speed of sound.
Related to the speed of sound, very good. So what's the speed of sound?
300.
Not necessarily, it might be different depending on the fluid. So it is like 300 meters per second in air. Also, weirdly, it's about 300 meters per second in outer space. Because the temperature goes down, but so does the particle mass. So a typical velocity, the thermal velocity, does that help if I call it the thermal velocity?
Sure.
What's the thermal velocity?
No idea.
No idea? Okay, so you remember when I have a particle of gas in my gas, and so this is one of those thermodynamics things that some people have seen some of the time, but not everybody has seen enough for it to be a knee-jerk reaction, so that's okay. This is one of those things that you should just like internalize. When I have a particle in air, its kinetic energy of the particle is 1/2 m particle, let's call it a proton, v thermal squared. And this is equal to the thermal energy in the gas, which is going to be 3 times K Boltzmann times the temperature. 3 because you have 3 dimensions. And KT because temperature is energy per particle. And K is what you turn, that's how you turn kelvins into joules. K is just a constant that relates the energy per particle with the actual energy. Have you guys seen this before? Yes? I have never seen that before? Okay, that's right. So if you haven't seen this before, write this down because this is key for lots of things. If you have a gas, the kinetic energy of the particle is going to be equal to the thermal energy of the gas. So we can say that the thermal energy is 3/2. Oh, I missed a half. Sorry. Where did I miss a half? I'm missing a half somewhere. Sorry, it's early and my caffeine hasn't kicked in. 3/2 kT over the mass of the particle. You get a square root of that. So the thermal velocity, let's erase that because I fucked something up there. The thermal velocity is 3/2 kT over the mass of the particle. So this relationship tells me what is my typical velocity in a gas. So this is going to go like, how much velocity is 3/2 kT, square root of that. And then how far can it go? Have you guys talked about an expression for how far a particle can travel in a gas? It's called the mean free path. Yes, I kind of heard of that once. Okay, cool. Yes, I know the derivation of it in my head. That's all right. Sometimes I ask questions that I know the answer to, so that's why I'm prepared to do it. So how far can a particle go? So if I think about a particle, it's got some velocity, it's got some cross-sectional area. We're going to call the cross-section sigma. So that's just how big it is, with big quotes. Cross-section is a deep rabbit hole that you'll learn all about when you take quantum mechanics and all kinds of things, because what's the cross-section of a bare electron? Well, the electron itself is really small, but the electric field extends out to infinity. So the electric field's pretty big. So cross-section's a funny thing to really get your head around, but just think about it as that's how big the particle is. And then it's going to travel a distance called lambda. That's the mean free path. And so the number of, so this sweeps out a volume in space, and that volume is equal to sigma times lambda. And the number of particles in this space is equal to sigma times lambda, that's the volume, times the density of particles. So this gives me the number of particles. And so if there's one particle in that volume, then I run into it. This gives me an expression for lambda. The mean free path is 1 over the density times the cross-section. And then there is a square root of 2. Really, you need to think about the relative velocity of the two particles. And the problem gets a little bit less simple than just writing down a volume times a density. So you get a square root of 2, but it doesn't really matter. So times the lambda, which is 1 over square root of 2 and sigma. So this only depends on the thermodynamic properties and stuff that's in the fluid. So sigma tells you is determined only by what the atoms are, more or less. I mean, we're not going to deal with relativistic fluids here. N depends on how I've constructed the gas. So the density is going to be, how dense have I made that gas by whatever means. And T is the thermodynamic pressure, or temperature. And T and N are, of course, related by the pressure, so there's some relationships that we can give. But this viscosity is going to be when I'm traveling, when most of the flow is traveling along this direction, some of the flow shoots off in this direction, and then brings some this direction momentum up with it. Does that make sense? Because velocity of a particle is going to be the stream plus the thermal, let's call this thermal now. The total velocity is the stream velocity plus the thermal velocity. So when the thermal velocity carries it over here, it's going to bring the stream velocity with it. Does that make sense? Think about it as a truck that's carrying some velocity, but the velocity is what's carrying it, so don't think about it too hard. So that's what viscosity is. It's the transverse motion of the fluid. So we assume, and this is where the assumption is. The assumption is that the shear stress is proportional to dVi dxj. So now we need to sanitize this to make it make sense. So we have this tensor that I've written down, but this isn't really good enough to do a lot of general math with. But it is the answer. So, so let's generalize this tensor a little bit. So this, here we get a little, yeah.
Why do you have no mass of the particle on the right hand?
Oh, yeah, because that one? Yeah, because I fucked it up.
So I think
That's a running theme, so I do apologize in advance. I drop things because I'm talking as I go, yeah.
And also, the equation that you had before, the 1/2 MP the thermal squared.
Right.
I think it's just equals 3 K Boltzmann T, because if you do that, then it's cheaper.
Yeah, that's right. That's what I think it is. But then I kept getting 4s because I was divided by too many 2s because I'm trying to do algebra in my head while talking to people, and it doesn't always go great. Detail, the square root of t is the important part. The 3/2, that'll just change depending on what actual particles you have.
I think it says 3kT by mv. There's no half there.
There's not a half there, that's my problem, thank you.
Oh, okay, so there isn't, so then there's a half.
Because this is why you write things down. Because 1/2 mv squared equals 3 halves kt, because you get a half per degree of freedom. Right, and then the halves cancel 19. Thanks. Squirrel brain. Okay. It's a collective action learning. We're all doing it together. So, okay, we've got this shear tensor, and now we need to sanitize it so that it's general and doesn't have any stuff in it that we don't want. So we're going to generalize it, make it super complicated, and then make it simpler again. Okay, so pi ij should be symmetric. Why? Because if I look at the universe and then I just flip the coordinates and I look at the universe the same, I shouldn't get any difference, especially when it comes to the shear of things. So if I have a shear like this, it's the same shear if I look at it upside down or if I look at it this way, or if I look at it right side, right? But so we're just going to say that this equals dVi dxj, but this isn't general enough. So let's generalize it. So the first thing that we're going to do is write it as a symmetric tensor and an antisymmetric tensor. And this is something that you can always do. Whenever you have a 2-index dude, you can always write it as a symmetric part plus an antisymmetric part, which is kind of magical. Like this could be some chaotic nonsense and have no symmetries whatsoever. We just pull this stunt and we say that this is equal to 1/2 dVi dxj plus dVj dxi. So I've swapped the indices. And here is the stunt, is making sure that I write clearly. Plus 1/2 dVi dxj minus dVj dxi. So many math proofs that you run into in life are just cleverly adding 0 or multiplying by 1. Here we're just adding a 0 in a way. So you can see that this dVi dxj is the same as this much more complicated thing. This guy adds up to this guy, and the halves cancel out, and this guy cancels this guy. This is the reverse. So now this part is symmetric. You can see that this is symmetric. If I swap I and j, these guys just swap sides, and I get the same thing that I started with. Whereas this term, if I swap I and j, I get the minus of what I had before. Does that make sense? Is everybody good with that symmetry there? Stop me if you're missing that. So I'm going to leave part of this for a homework assignment, but this part is rotation. And we only want to talk about the shearing motions and not the rotation motions. So you can recognize this as a component of the vorticity. Is that clear? Because it's the cross derivatives and they're subtracted from each other, just like a cross product, just like the curl cross product. So this looks like the curl of V, which, as I said last time, is like the rotation of the fluid. This is, again, the rotation of the fluid. So this is not the term that we want. So we're going to just throw it out. So we're going to say that pi ij is equal to 1/2 dj vi plus di vj. So now we only have a symmetric tensor. Everybody good with that so far? Yeah.
Why can't you just throw it out?
Well, so we're trying to model what the viscosity looks like, and we don't want the rotation in the thing we're using, because that's going to be double counting, because we're already taking care of what the rotation is doing in this term.
Okay.
So if I add this, then it's double counting.
Okay.
So I need something that looks like this, but isn't this, because this by itself isn't symmetric.
Okay.
So this by itself depends on how you're looking at the world. But this one is symmetric. And so that's the thing that we want. So we're going to say that our general tensor is this. Now, the most general way you can write this down, so this has, let's talk about this guy. It has terms along the diagonal and then terms off the diagonal. So when I make the transpose, the off terms get flipped around, and the diagonal terms don't. So the diagonal terms need to be treated special relative to the off-diagonal terms. And I want this to be rotationally invariant. So when I swap I and j, however I'm going to swap I and j, I get the same basic term. I get the same structure. So this can only depend. So as I swap I and j, I'm going to swap the order of these three things. And so these three things, the actual tensor that I'm going to use can only depend on these three things in sum. So it has to have some a times div v plus b. Did I do something wrong? No. So a times dj vi plus di vj plus b times div v is going to now be my pi ij. So this is actually the most general second-rank tensor with all the symmetry properties that we want, that one can write down. And you can see that, you got to kind of stare at it and be like, what, really? That's the most general thing you can write? It is. So there's nothing more generic that you can write that is a second-rank tensor that's linear in all of the terms and is independent of rotation of the indices by themselves. So it's got two terms. It's got a thing that looks like the cross derivatives, and one thing that looks like the divergence of the velocity. Yeah.
Can you explain the variables, because I can't see.
Yeah. I'll just write it bigger.
Okay, thank you.
So it's a times dj vi plus di vj plus b times div v. Now really I can write this as dk vk, but it's a little bit easier, a little bit more instructive to leave it as the div, because div has special properties.
Thank you.
So this is the most generic tensor that you can write. But I already know that the diagonal term of my pressure tensor needs to be the gas pressure. that make sense? So I'm going to write something that looks like this. It's going to have a pressure along the diagonal and then my shears. So the gas pressure, if I take PII, the trace of a tensor is just the sum of the things along the diagonal. The trace has got to be 3 times the pressure. So you just need to have the pressure on the diagonal. So that's what the sum of the diagonal terms has to be. So we have to write this in a way that doesn't have a trace. Okay? So we need to say that what we're going to say, we're calling this pi ij. We're going to say that pi I has got to equal 0. So you just do that, and I'm not going to do it because I'll leave that algebra to you guys. What that shows you is that B has got to equal -2/3 A. So now we can write down a slightly more generic or a useful tensor. We're just going to write this down as minus mu times di Vj plus dj Vi minus 2/3 delta ij div V. So this is kind of the stopping point for now. So here we've written down a tensor that does what? What does it do? Linear in djvi in all of those terms. 2, it's symmetric and rotationally invariant. And 3, doesn't mess up the pressure. So it's linear in the derivatives of the velocity. It's symmetric and rotationally invariant, and it doesn't mess up the pressure. So we need those things to be true to write down what our momentum transfer term is going to look like. So after we've done that, then we're left with this, which is kind of gross. We're gonna do a little bit of calculus and make it simpler in like 1 second. So I'm going to leave this up here, and I'm going to get rid of all this. And we're going to write, now we can just write an equation. So now I have this, now this is true. So we're going to take this, where my pressure tensor is this guy. So I've got my gas pressure along the diagonal, and I've got my shear tensor that it has diagonal terms, but they all cancel out when you sum everybody up. So I'm going to write full derivative dv dt equals let's put this rho here. Full rho times the full derivative of dv dt is grad p plus, we're going to do the same stunt. This is the top dA, so we're just going to integrate by volume, and then the volume turns into a gradient. The area integral turns into a gradient of the volume integral. So I'm going to take this term, but I'm going to have a d by d I on this. So we've got, this is vi, this is dip, and there's a minus sign there, plus mu times d by dj of di vi plus dj vj minus 2/3 delta ij div v. Oh, I'm sorry. I wrote this wrong. dj mu times all of this. So I haven't said why I can take the mu out. So this is most general, but not most useful. So let's simplify this a little bit. So we're going to pull this derivative through everybody. And when I take, this is a dj on, this is di vj, and this is dj vi. So this guy on this turns into like a divergence because it's a dj and a vj. So it's going to combine with this term. And this term on this term turns into a mu del squared v. And then the combination of everything else turns into a plus 1/3 grad div v.
Is it rho?
No, there's no rho here. The rho's over here.
Oh, is
Now I'm going to put the rho. Now let's get the rho over here. So I get a 1 over rho here, and now this is a nu. So that's the difference. Yeah.
So the negative sign from the Pij, like did you carry, I'm sorry, the Pi ij, did you carry that in there? Like,
Here? Yeah. So that turns into a plus here because of the minus here.
Oh, okay, okay.
Does everybody follow that? So the most general thing we can write now is d by dt of v, and this expands to this thing, equals minus 1 over rho grad p, that's what we had before, plus whatever forces you had, plus nu del squared v, plus nu over 3 div v. This. It's still not bad, but it's pretty close. The only thing that's extra is this last term. This last term is called the bulk viscosity. Now, it depends on div v, and div v has this special place in the fluid dynamicist's heart in that it's 0 for most fluids that you're dealing with. It's hard to make the divergence of a fluid positive with just a flow. You can do it if you have a boundary condition or you're pushing on it with like a piston. But with a flow, it's really hard to make the density go up. It's really hard to make div v not 0. So this last term, we almost always throw out. And I work in supersonic fluid dynamics, and we throw that term out too, which is the only place that it would ever show up, is when the flow is supersonic. So now we're left with Navier Stokes. We have dv dt, we have the pressure gradient, and now we have our viscosity term. Are we happy with that so far? All right. Is there anything else I'm supposed to say? No. So we're going to use mu. We're going to use nu basically all of the time, unless we have the momentum equation. So we can write down an equation for the momentum, which is just taking Navier Stokes and writing it as rho v. So let's do that real quick. So I can get an equation for the momentum, which is sometimes what I need. V is not a conserved quantity, and often you need to be doing your math with conserved quantities. So I do a lot of computational fluid dynamics where we take a volume of space and break it into cubes and do fluid dynamics on all those little cubes. And there, it's important that you keep everything conservative, because that way you're not suddenly losing momentum through the course of your evolution. So let's look at what d by dt of rho v is. So just by product rule, this is rho d by dt of v, plus v d by dt of rho. And I should have written up continuity. Let's do that here. dt of rho plus div rho v equals 0. So this is just v dot minus div rho v. And this term, dv dt, is going to be minus rho v dot grad v minus grad p. And then I also have a plus mu, because I'm multiplying by density, del squared v. So this is just a pressure term, and nothing happens with it. It's just a pressure term. But this term is rho v dot v, and this term is v dot rho v. So if I have a grad v plus b grad a, what is that? Simplify that for me. Just, it's integration by parts. Just integrate by parts backwards.
Oh, grad AB.
There you go. It's just grad AB. So d rho v dt, so the derivative of the momentum with time, d by dt of rho v equals minus grad p, no rho, plus mu del squared v minus div rho v v. Now, you may hate this because I have written two vectors that I have multiplied together. And that is not obvious what that means, right? You don't know how to multiply vectors. That's not a thing you do. There are extensions of math where you can multiply vectors together called geometric algebra. It's very interesting. Probably useful, but not for us.
What does that mean?
So what does that mean? So what this means, it's easier to see it. You'll see it written in textbooks this way and papers all the time. The easiest way to think about this is thinking about the indices. So if you just do this with the indices, then you're left with, actually I'll write it up. I'll write it up here so everybody can see it. d by dt of rho vi plus d by dj of rho vi vj equals minus di p. Did I get everything? Oh, minus. Plus mu dj squared vi. So I'm writing a vector equation, so I've got one free index. That means it's a vector, so this one is I. So here, I've got a contraction of my divergence with one of my velocities, and then my other velocity has the I component. So the derivative is acting on the same component as one of the velocities, and the other velocity has the same component as the velocity that we're taking. So it takes a second to think about this. You can think about this as the velocity tensor. It's Vx, it's a tensor, Vx, 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 Vy, Vx, Vz, et cetera, et cetera, et cetera. Or you can think about it as these two individual components, component-wise. Thinking about it as a tensor is a thing people like to do, but it's not really all that useful. Sometimes it's useful. So this is a little hairy because now we've really got to start paying attention to what our indices are and which vector components are getting dotted into which other vector components. I drop it like it's hot running through my head. Okay, so doing physics is all about throwing out stuff that you don't need so that you can solve the problem. So we're going to throw out various terms of this in various situations. Actually, let's write down Navier Stokes too. dt of v plus V dot grad V equals minus 1 over rho grad P plus nu del squared V. So there are two important terms in this equation. dV dt is just like what you're looking for. So that's just the answer that I want. This is what I care about. That's not. Grad P is just what's going to happen. Like, that's just how you're pushing on the stuff. There's not a lot of magic in it, but there's a lot of magic in this V dot grad V term, and there's a lot of magic in this nu del squared V term. So if you remember from last time, I talked about flow past a cylinder. And in Euler's equation, a cylinder can move through a fluid without any dissipation, just the slightly larger effective mass. So that comes out of that flow around a cylinder term. And what we showed was, what I showed with the von Karman street is that as you increase the velocity, it goes from this really simple laminar flow to something that starts shedding vortices in this complicated manner. And the difference between slow flow and fast flow, you can see in this equation. So we have these two terms, and the units on this term, let's talk about the units for a second. The units on this term, what are the units on Navier Stokes equation? What's the units on this? This is meters per second, right? So the units on this, I've got velocity squared divided by a length, which is going to give me meters per second squared again, because this is meters squared per second squared, and this is one of those meters, so we've got meters squared per second. And this guy has a viscosity times a velocity over a length squared. Because think about the derivative as just 1 over a length scale squared. And when you're doing physics, think about derivatives as just 1 over length scales or 1 over time scales. That helps you get to the answer faster. So I can relate these two things and take a ratio of them, and this is called the Reynolds number. And it's it's the ratio of the kinematic term, or the kinematic or the nonlinear term, over the dissipation term. So if I take a ratio of this over this, I've got v squared over L over nu v over L squared. So the Reynolds number is equal to the length times the velocity divided by the viscosity. So this is a crucial number for several reasons. Two really important reasons. One, is it lets you rescale the equation. So if you look at Euler's equation says d by dt of velocity equals minus 1 over rho grad p. And if I change meters to kilometers and seconds to gigayears, this equation doesn't change because all of the units just cancel out. So I'll do this as d by d time times gigayear, and then I have to have a similar kind of term over here, and my units will all cancel out because I'll have to change the time that enters into the pressure as well as I'm rescaling the units. So I can rescale the units on Euler's equation without changing the equation. But in Navier Stokes, I have this nu, and this is a physical constant that God has given us that tells us about how the fluid behaves. And if I change the units on everything else, I can't change the units on that because that's a physical constant that is unavoidable. So all I need to do is rescale the process, keeping this relationship constant, and I can make a tiny little airplane that behaves just like the regular size airplane, which is really useful because building a wind tunnel is hard, Building a wind tunnel that can fit an entire 747 is really hard, but building a wind tunnel that can fit a 747 that's this big is pretty easy. So what do I need to change if I'm going to try an experiment where I want to decrease the length by a factor of 10? Now, this is a little extreme, but what do I have to do to the velocity to keep this constant? Increase it by the same factor. So so I can make a smaller scale model, I just have to increase the velocity over the object. Yeah.
So length in this case has to do with the size of whatever, like what is length?
Yeah.
Yeah.
Yeah. I don't have a good answer for that.
Okay.
It's the length that matters the most for the system, and you can generally be pretty vague because if you pick the wrong one and the Reynolds number is large, you're still typically going to get a large value. So one of the homework problems that's coming up is sort out what the Reynolds number is for various situations, and coming up with what the relevant length scale that you think is kind of a free parameter. So there's no L in here. There's not a length in here. The length is kind of hand waving in the derivatives. So when I talk about an airplane flow, I've got the wingspan. So that's probably the most relevant quantity. But you've got to think that when I'm rescaling the plane, all of the size scales are going to rescale the same. So you just pick one. It kind of doesn't matter. So on one hand, what you pick for L kind of doesn't matter. But on the other hand, it's crucial for getting the right number. But also, this is a ballpark number. This is a feelings number. This isn't something that you can do any real calculus with. But that means, but it's still very important. Because we can talk about a low Reynolds number flow. So a low Reynolds number flow, which term is going to be dominant? This term or this term? If the Reynolds number is small. Right, the viscous term. So in low Reynolds flow, the viscous term dominates. So typically you can throw this term out. In high Reynolds number flow, you can typically throw this term out because the high Reynolds number is means that this term is going to dictate what's going on in the fluid far more than this term. Which is also why I throw this term out, even though in my supersonic studies, the divergence of the velocity is really large. It's still really small compared to the nonlinear term, because my Reynolds numbers are factors of 1,000. So when you get to a Reynolds number of like 1,000, things start to get turbulent and complicated. Yeah, so let's see. What have we done so far? We've done Navier Stokes with all the tensors. We've done momentum. Now we've done Reynolds number. And the Reynolds number is going to come up over and over and over again because you can do so much with it. It's such an important quantity. Let's see. I totally misjudged how long this was going to take me to get through all that. Oh, I still got like 20 minutes. That's cool. That'll be the next part. So I'll come back after you guys have done the reading. I'll come back and touch on all this again so that then you've gone over it once with me, once through the readings, and then I can answer all your questions about all of this nonsense. Because there's some tensor stunts that are confusing a little bit, but also kind of generic. Like these are stunts that you'll see whenever you deal with tensors. When you get to field theory, you're going to pull tensor stunts like this too. When you get to GR, you'll pull tensor stunts like this too. So let's talk about flow through a pipe and what that means for Navier Stokes. Navier Stokes, viscosity, Reynolds number. me 1 second. I gotta reorient my brain. I was only half thinking about talking about this today, so I didn't go over it this morning. So now you gotta wait for me to make sure I don't say anything stupid. Yeah, okay. So if you have flow in a pipe, so say I've got some pipe with a radius A and a length L. You're right. So we're going to say we want to just know what the steady flow is through the pipe. So we're going to erase this term, but we're going to consider, oh, sorry. We're going to say that the flow is steady. Also, because it's a pipe, I can say that this term, unless something bad is happening, this term is also going to be 0 because the velocity on this side has got to equal the velocity at that side. So the velocity, so this is a gradient of the velocity along the velocity. I've got the dot product of two things, so it's a projection. So this is the projection of the gradient of velocity along the velocity. I know that that's going to be 0 because whatever I put into the pipe has to come out. So the left-hand side is 0, and I'm left with just the right-hand side. So I'm left with just minus 1, let's see, put that to the other side, 1 over rho grad P equals nu del squared V. And we can pretty helpfully say that let's call this Z, that Vx and Vy are 0 because otherwise they would go through the wall of the pipe. So those are 0. Now, when things get chaotic, this stops being true. So if you start to push the flow through the pipe so the Reynolds number becomes large, everything that I'm saying falls apart. Because you have a spontaneous symmetry breaking and this symmetry is broken. But we can just say we only have a z component of the velocity. And so we put this mu over here. So let's get rid of rho and call this mu. And now we just have grad P equals del squared V. So we're going to call this delta P over the length is equal to mu times, okay, you got to look up what del squared is in cylindrical coordinates. Does anybody remember del squared in cylindrical coordinates off the top of their head? You will when you're done with the ENM, but yeah, that's not required now. So it is 1 over r d by dr r dv dr. Okay, so now all we need to do is just integrate this ODE. So I just have a, yeah.
Is that delta P?
Yeah, this is delta P. So this is the pressure. So I'm integrating the pressure across the length, so I just get the pressure difference. So this is the pressure difference from one side to the other divided by the length. So it's just a proxy for grad P. But a proxy for grad P that tells me the pressure per unit length, because if I make the pipe longer, things change a little bit. But really, it's independent of the length of the pipe. Yeah.
And also, is that mu 1 over r?
Mu 1 over r, d by dr, r, dv dr.
Okay.
So this term, this is del squared in cylindrical coordinates. Which at times I've made you guys rederive just because having an opportunity to sit down and see where that comes from is super useful. I haven't written the next homework. Next homework should come out tonight, knock on wood. So now we just need to integrate this. So we take an r and we put it over here. So I get, let me give myself a little bit more board real estate. So an r goes over here, and we're left with r delta p over length equals let's pull a mu over here too. What do I want the mu? Yeah. Equals d by dr of r dv dr. So I just put all the crap onto the one side. And now I can integrate both sides. So when I integrate this side, that goes away, because I'm just integrating a full derivative. And when I integrate this side, all I have is an r, so that becomes a 1/2 r squared, delta p over mu L equals r dv dr. So now I cancel out an r again, and I integrate again, and I'm left with 1/4 r squared delta p over mu L equals vz. So, so this tells me that my velocity profile depends on radius like this, in that, so if I have a pipe, oh, I forgot to talk about boundary conditions when I integrated. So what are the boundary conditions with that I integrate? Is that the velocity has to be 0 on the surface. So there's two velocities. So Vx and Vy are 0 at the edge because they can't go into the edge. And Vz is 0 at the edge because you can't have shear against a solid wall, because the solid wall can't move. So the velocity immediately at the wall also can't be moving. Then you build up a shear layer from there. So the boundary condition is that the whole velocity on the wall is 0. And the gradients of the velocity at the center have to be 0. Yeah?
So you always have that like layer of non-moving water in that pipe?
Yeah. There's always a layer of flow. It's not very thick.
I mean, yeah.
But there's a boundary layer. So we talk about the boundary layer. So the pipe flow in this scenario, the pipe flow is parabolic. So it's 0. So if my VZ axis is in this direction, it's 0 at the walls and maximum in the middle, and looks basically like a parabola. Yeah.
What did you say VC is equal to?
VZ
Yeah.
is equal to all this.
Oh, okay, okay.
So this is the profile. So it's got my R dependence. So I've got my pressure gradient, my viscosity, and then my where you are in the pipe. And so it's maximal in the center. So we can talk about the flux through a pipe. So if we talk about the flux, which is Q, is the integral from 0 to A of rho V times 4 pi R dr. So here I'm just integrating rho V. Rho V, remember, is the flux of mass. So this is just rho V times the volume times the area element. So I'm just going to integrate that. I get that the flux is pi over 8 times delta P over mu L times A to the 4th. So the amount of water you can put through a pipe goes like the area, goes like the diameter of the pipe to the 4th power. Not linear in the diameter of the pipe, and not like the area of the diameter of the pipe. It goes like the 4th power. So a bigger pipe gets you a lot more flow because of the wall effect, because the wall's further away and you can carry more stuff. Now this only works until the Reynolds number gets large, and then it starts to become turbulent. And then the pressure changes, and then this pressure relationship. So you can think about this as the profile of velocity, or you can think about it as the velocity that you get from a certain pressure. So as I keep increasing the pressure, the flux goes up linearly in the pressure and then starts to oscillate, and as I increase the pressure past a certain point. So past when the Reynolds number becomes large, I can't push as much fluid through the pipe. But when the flow is slow, then I can get a lot of flow through the pipe. Let's see. 15 minutes. Yeah, I'm talking way faster than I think I will. Yeah, and the thing, I'm not gonna do lift, I'll do lift next week. I'll do boundary layers next week too. Have you guys seen complex integration in math physics? Do you guys see removal of poles by Cauchy's? Kind of as a mid. All right, I'll talk about that too. Mostly I'm going to talk about it because it's useful math. We're not going to use it a lot, but sometimes when you're trying to do an integral, there's a 1 over x that you can't integrate around. But if you make it a complex integral, then you can just go around that 1 over x and then send where you're going around it to 0. And you can do an integral that you wouldn't otherwise be able to do. It's a very cool thing. So we'll do that. So there's a reading, skip the accretion disks in astrophysics unless you're really interested in that. We're not going to do anything in rotating coordinates this semester just because there's only so many things that I can do. So I'm skipping those bits to get to other bits. Yeah, I think I talked too fast, and that's all. Does anybody mind if I stop 10 minutes early? Does anybody have any questions that I can talk about today? This is all the stuff that I wanted to cover today. So, does anybody have any questions about anything? Feel pretty good. Yeah.
That R, like logically, if you plug in 0, you get 0 velocity. So should that be like R minus A or something?
Oh, yeah. I wrote that down wrong. Good eyes. This is what I get for going through the calculus fast. So I went through this calculus too fast and fucked up the boundary conditions. So you guys should all be upset with me about that, because this is totally wrong. This should be a squared minus r squared. Should look at my actual notes.
Because you're integrating.
A squared minus r squared times delta p over 4 mu L. Yeah. So, thank you. Duh. That's what I get for being a nerd. Keeping you on your toes by being an idiot. So, all right. Any other questions before we part ways? Yeah.
So is this the stuff they use to like design planes and stuff like that?
Yeah, exactly. So everything comes down to Navier Stokes. And you know what nu is for air. So you just rescale and you can simulate this, or you can use it in a wind tunnel. Yeah.
If there's like fluid on the outside of the pipe, on the boundaries of the outer edge of the pipe, is the fluid not moving there as well?
I mean, if I have you mean if I have fluid here?
Yeah.
Yeah, I mean the fluid's rigid. The pipe is rigid. So you can't transfer momentum through the pipe. Unless your pipe is like soft, then that's a totally different class. That's soft condensed matter is a complicated topic.
Is that like graduate level?
Yeah, I don't think there's a graduate soft condensed matter. That's an invent it yourself, I think. There might be, but I don't think we have one.
Gotcha.